Sujata madam to briefly introduce our resource person of the day. Sujata madam, can you please take over? Sujata madam? Answer sir?
Sir, madam is there, sir, but not talking.
Co-host ఏమన్నా ఆవిడకి మేడం గారు
Sujata madam. Sujata madam. Sujata madam. Sujata madam.
Hello, Nanchali sir, am I audible?
Yes, sir. Yes, sir.
Yeah. So good afternoon, sir. Good afternoon to all the participants. There are some technical glitches due to which Madam could not turn up. So I take this opportunity to introduce our resource person, Dr. Devi Prasad Dogra. Dr. Devi Prasad Dogra is an assistant professor of computer science engineering in the School of Electrical Sciences at IIT Bhubaneswar. Sir received his PhD from IIT Kharagpur in 2012 and got his MTech from IIT Kanpur in 2003. Sir finished his BTech from HIT in 2001. Earlier, Sir worked with HIT Haldia as a faculty member, Electronics and Telecommunication Research Institute, South Korea, as a researcher, and Samsung Research Institute, Noida, as the research group leader of Advanced Technology Group. Sir has published more than 100 research papers in international journal and conferences in the areas of visual surveillance, image understanding, computer vision, augmented reality, intelligent transportation systems, HCI, and healthcare analysis. Sir is an editor of Springer Nature Computer Science, SNCS, and Journal of Multimedia Information Systems, journals. Sir is currently serving as the Joint Secretary of IEEE Bhubaneswar subsection and Vice Chair Technical of IEEE Communication and Computer Joint Societies Chapter, ITR Chandipur. Sir is a member of IEEE. So now at this juncture, I am fortunate enough to introduce our resource person of the day. Sir, now may I request you to take over the session and start enlightening us, sir.
Thank you. Thank you, Dr. Sudha, for the introduction. So, is my screen visible?
Yeah, sir, it's visible, sir.
Okay. So, thank you, sir, for this introduction and for giving me this opportunity to, interact with these faculty members and participants in this, short-term program. I hope that this particular discussion presentation will be beneficial for both the participants and myself through interactions that will be happening during next 2 hours or so. I shall be happy to get your questions at any point of time. If you would like to ask, you can ask me, or if the moderator decides that it will be toward the end, that is also fine. Okay. So let me start my talk. As Dr. Sridhar mentioned, that the topic is AI and ML for visual surveillance. So I shall be mainly discussing the research work that we are carrying out and what the other people across the globe they are carrying out on this particular domain. Okay, I shall try to focus more on the AI and ML part, because that is the main theme of this short-term course. Okay. However, before we proceed to the to understand the applications of AI and ML, we must understand that what is visual surveillance. So, visual surveillance is a terminology that is very close to computer vision. Okay. So, if you try to understand that how we humans or any animal who are capable of seeing through the eyes, how do we perceive the scene and how do we recognize the scene? Okay. Now, when computer vision is taken into consideration, then computer is a machine. So we need to understand that how a machine can understand the scene. Okay. So in layman's term, we can say that this is the science and technology of machines that see. So how a machine sees. So it is concerned with the theory for building artificial systems that obtain information from images. the image data can take many forms. It can be in video sequence, it can be depth images, it can be multi-sensor data, multi-dimensional data, medical images, like X-ray images, MRI images. Okay, so and CT images. We can have different types of images available. Now, we humans, if we assume that we are intelligent people, that's because we are able to understand these images. Now, it's this understanding, even if you look into that human understanding, it is not happening in one day or in one minute or 1 hour or within a stipulated time. We have been learning all these things since we are born. So that means there is a parallel system which is running, and that system is every day getting updated from the inputs taken or captured through the sensors available with our physical body, and these inputs are processed by a very strong or powerful computing device which is there in our brain, and then the brain understands it or takes decision. Okay. Now, when the same thing you would like to do it for a machine to do, you need several components to be accurate there. Now, why it is very difficult, for a machine to understand image? Let's see, try to understand the basic things from this image. Now, if you look into this image, if I ask a question about this image to 100 people, I can ask 100 different questions. The questions can be, what is the color of the sky? What is the color of the cloud? How many trees are there? How many cars are there? What is the color of the second car? How many types of flowers you can see? Okay, so I mean to say that you can generate hundreds, thousands, and possibly millions of such questions. And each and every question can be, you may have different answers for each and every question. Now, even if you ask a human being to answer these questions, that person may be, you can assume that the 90% questions may be answered by a human. Okay, or 10% will depend on what kind of human he is, whether he knows everything about this image, something like that. But still, there is a chance that a human will be able to answer any one of these questions. That's the reason is all the objects, their presence, their locations. Once we see the image, we can instantaneously, arrange these objects in our mind, and we get these relations ready into our mind. Like the white car is toward the left side and the other two cars are toward the right side. So these sort of relations we automatically create in our mind. Like there are, primarily 3 colors of the flowers I can see, all these things, and sometimes these questions, these, answers are, generated based on the question instantaneously. Okay. But how do we basically ensure that a computer understands this? Like what kind of scene? Even this what kind of scene, if you ask human being, 10 human may give 10 different answers. It is likely that some of them will be common, but it is also possible that many of them will be giving different answers. So there, it's very difficult to tell that which one is actually correct and which one is, partially correct and which one is not correct, because this is also subjective in nature. One human looks into this as a car parking perspective. One human looks into okay, this may be a resort in a place for staying. This may be a park area, something like that. The answer can be many. Okay. So it means the ambiguity is there even to the humans. If the ambiguity is there to the humans, that the same ambiguity is, multifold, it's present with multifold with the computers. So if the first question, if you try to answer that what kind of scene, the computer, may give a vague answer or may give an answer which you may not like. Like second question, where are the cars? that even where are the cars, the cars may be located at different places. So which will be the correct answer? That itself is subjective in nature. So if it is subjective in nature, then even the answers which you are getting it from a human being is also, you cannot assume as a holy grail or ground truth. It will vary person to person. Okay. Then how do you expect that a computer will give the perfect answer? That's why it's much more challenging. Similarly, the question is how far is the building? Okay. So how far is the building is a question that can be answered in many ways. Whether the building is how far from the two paths, the building is how far from the observer who is seeing the image, or whether the building is how far from the center podium. I mean to say that center statue. So there can be different opinions. Okay. So if you want your computer to understand all these relations and try to answer every possible way a user will give an answer to a question for this particular image, then it is really, it's an amazing thing. And if you are able to solve it, it probably solves many of our real life challenges. Okay. Now to do that, what are the components we need? If you want a computer to understand, I mean, this is what we are talking about, visual surveillance. Visual surveillance means a computer will see and computer will understand and computer will take some decision. Now, how the computer will see? Computer has no eyes, so you'll have to create the eyes or you'll have to attach the eyes with the computer. That's why in a typical computer vision system, you'll find that there are three components. Active components I'm talking about, active components. There is a passive component also. That passive component is basically lighting. Okay. The active component is basically camera, which is a sensor. Then you have the computing power or the brain, and then you have the scene. Now, when the light is incident on the scene, it gets reflected, and the reflection is captured by the sensors of the camera. And that sensor sends the data to the computer processes it, and computer understands it. So these three components are very important in a typical visual surveillance computer vision system. Okay. Out of these three systems, two are part of the surveillance system. Three is the third one, which is the scene, is outside the computing system, but it is also part in the entire closed loop operation here. Now, how it is different, how it is different and how it is hard. If you see on the left side, there is an image. And we humans see this image like this. Okay. And we interpret accordingly. It may be, somebody may interpret as an accident image, somebody may interpret as a sculpture image, or I mean to say that there are many ways you can interpret it. Okay. Now, if you look into the right side, I've just given it a numbers which are not binary. It's a decimal numbers, but actually it's a binary numbers. So a computer sees all these things as an array of binary numbers. Now, on the left side image, you may be able to mark the engine rightly or properly with a pencil, because you know that what a boundary means. You know that what is the meaning of an engine, which portions are the part of the engine. Now the same thing, if you would like to try to do it on the right side, you may not be able to do it, because that boundary patterns and how the pattern varies along when the boundary is matching with the wall or the boundary is matching with the railway track. So finding those edges are very difficult in a binary image. But computer will only understand that. So what you need to do, you need a mapping between the left side to the right side. So if you are able to generate an efficient mapping that solves this particular problem, then actually we are done with the vision part, and which solves the problem in hand. And if you are able to solve it, then I think life will be very easier for us. Tomorrow, if there is a computer available or there is a vision system available which recognizes everything at every angle, every scale, at every length, then I think problems are solved. I think 90% of the problems which we face, which we do, okay, they will be solved. Because vision, if you look into it, and why it is important, because if we do not have eyes, then possibly we have nothing to do. I mean to say that there are people in this world who may not be having their eyes, or who have lost their eyes due to some accident, due to some other difficulties. But you think about that, how without eyes, how those people are living. It's basically, if every people in this world they are blind, then it doesn't make sense of making any object. Okay, it doesn't make any sense. So, if you look into the science behind this, okay, first we need to understand the hardware. Vision is a really amazing feat for natural intelligence. If you go into deeper, you will understand that visual cortex occupies more than 50% of a typical macaw brain.
Hello, sir.
So it says that more human.
Hello, sir. Devi Prasad, sir, I'm sorry to interrupt you. Your presentation is not visible, sir. Your screen is not visible, sir.
Sir.
నాన్సరే గారు సార్ జాయిన్ అవుతాను అక్కడ ఏదో ఇష్యూ ఉందండి ఇప్పుడే నాకు ఫోన్ చేశారు
ఓకే ఓకే సార్
నేను మాట్లాడాను ఇప్పుడే
ఓకే సార్
My dear participants, I guess there is a technical glitch on the resource person side. There is a network issue. He'll be rejoining back within 2 to 3 minutes. Kindly bear.
Sir,
Yeah, sir
sir
is back
already
now.
joined, sir. Sir,
Okay, right, right. Very good, very good.
Yeah. Am I audible now?
yes, sir. Yes, sir.
Yeah, sorry, there was some network disconnectivity from
Yes,
my
sir.
side maybe. Okay. So let us continue our discussion. So, so essentially what I was talking about is that vision is really a hard problem. If you look into it, that the vision, visual cortex of a typical of a macaque brain typically occupies 50% of the visual cortex. So that's a huge. I mean, so that you have 50% of the brain is occupied only to process the visual related things. That itself tells the story how important it is. Okay. So, so human brain is devoted to vision than anything else. That's it. So that is the bottom line. So if you want a computer to understand everything, the scene, you need to make the computer intelligent like humans. You'll have to do a lot of processing. And if you further dig into the domain, you'll find that it is multidisciplinary. So you need knowledge on artificial intelligence, robotics, machine learning, mathematics, neurobiology, imaging, computer graphics, signal processing, okay, cameras. There are lots of allied sciences and topics which you need to know if you want to be an expert in computer vision. Okay, if you not one person cannot be an expert in all these domains, but if you want to build a computer vision system which is as like as human, you need experts from all these domains. That's what it says. Now, why it matters? If you are able to develop a smart system which is close to humans, then you have better solutions for such scenarios. For example, safety related things, you can understand that automatically understand that where the accident has occurred. Even the car can automatically take a decision, like autonomous cars. Okay, when the car will automatically see that some objects are coming, something like that. Even the health, for example, tissue images. Okay, you want to understand cancer cells. Then the security, somebody is stealing in a shop or somebody is trespassing, it can be used in comfort, fun, even in access. Okay, so it means it has applications everywhere, starting from nuclear science to home science. Now if you go back to search into the earlier research on that, Bell Lab started this one very early, okay, to do digit recognitions, automatic digit recognitions. Okay, they have all started with recognizing handwritten digits and how accurately it can detect it. Okay. And then gradually it has moved to object recognition, scene understanding, all these things. And these sort of applications are very common these days. You will find face detection camera. So once you focus your lens toward a particular group of people, it will try to understand that where are the faces. Possibly the intelligence is these days, the intelligence is much more that they will identify that who is the person. Okay, like if I am there and if I see my colleagues in a meeting, okay, so my brain will be able to understand that, okay, this is my colleague, this is my colleague, this is somebody X, this is XYZ, this is ABC. Okay, similarly, if the camera is intelligent enough, the camera can also tell that this is a person, you should not take a picture of the person because the person has objected about taking the picture last time when you tried to do that. That's called intelligence. Okay. Say, for example, I have a camera, I go to community meeting and I started clicking photographs. Then suddenly I saw a couple of friends are talking and was trying to capture a photo, then I remembered that last time I came here and I tried to take the photographs, these people objected. So I remembered it. So intentionally, I do not take the photograph of those persons because I remember that last time when I tried to do that, they actually did not like it. So if you are able to make a camera that is smart enough, that will also try to do that. No, last time you did it, but there was problem like this. That's called, bringing intelligence into your computer vision system. Okay. Other examples like, smile shutter. These are very common these days. I was seeing that I think Samsung or LG came up with new mobile phones these days. It's getting an advertisement is coming that by they focus on your left eyes and it tries to, zoom in. Whenever it finds your eye properly, it will take a photograph, something like that. So I mean to say that these are all smart features coming every day, and that's possible because of the incorporation of the artificial intelligence modules within the camera device. So you are making the camera more intelligent. Like this, in a shopping mall complex, somebody is basically carrying all these through the carrier trolley, then you don't need to go to the counter. It will automatically understand that what are the things there in your trolley. So it will automatically identify the objects and get their price value, and the bills will be generated. Okay, so you do not need to go to the queue, and once you you are going out with your trolley, automatically it will detect that how many packets are there, what are their brands, what is the product, what is the price, and everything. These sort of things can also be done. That's a very smart thing to do, but if it is done, actually you are solving a lot of problem. Vision also rescues us in many cases. For example, if you look into these two photographs, this Afghan girl was identified by her iris pattern. So if you go through this story, this iris pattern, if you look into by naked eyes, you may not find similarity, because we may find all the iris girls, their eyes will be similar like that. No, actually when they did the analysis, the patterns, when they analyzed the patterns, they found the match between the girl's iris and her mother's iris. Okay, that is the advantage of having computer vision, smart vision, and intelligent systems to do the job for us. Other objects like this, object recognition, you focus your camera toward a scene, you get to see that what is that object. Okay, like in sports also, you want to see only the highlights of the scene. You have missed the rugby match. What you want to do? Okay, I would like to see only the portions when there was a fight going on, or when so and so blah blah blah. Okay, so you can intelligently generate the highlight without going through the whole 2 hour, 3 hour, 10 hours video. You just want to cut down those portions of the video which are important to us. Okay. Then this one I was talking about, Google cars. Not only Google cars, there are many companies. Tesla is trying hard. All top brands, they have started building cars by housing cameras across different directions and trying to understand the scene around them, so that the car can take its decision by own while the car is being driven. Okay, but I feel all the applications which I have shown earlier, they are mainly, they need some more refinement before they can be deployed without any risk to the human life. For example, autonomous car. I feel that we need another 50 years to do the research before it can come to an American road, fully automated. I'm talking about, they may call tomorrow that cars are running on the American roads, but it will be running only 5 kilometer stretch of American road. It's not the whole America. If they show us that it's working on New York, Times Square every day, every time, then I will accept that. So then only it becomes a solution. And if you want it to come to India, it will definitely take 50 years, because Indian roads are more difficult conditions. You will see, cattle roaming here and there. People are not following rules. People are not following zebra crossing. Okay, so how do you expect that autonomous cars will run here? It's not possible at this stage. We may have to wait for another 50 years. Okay, but where it is possible and where it is being done is possible with these industrial, assembly lines, because there's no risk involved here. It's basically the place is a fixed place. You don't want somebody will be entering into the place without proper authentication. Only the designated persons will be, traveling to this place, and they will be only going to the particular portion of the place. So if you have a fixed camera setup to understand the orientation of the car, understand the position of the robotic arm, it is very easy to do it. That's why assembly line things, all the processing, wherever it is possible, okay, computer vision based industrial robotic arms can solve a lot, and this is being done. This is being done. If you look into the modern refineries, I was actually having a discussion with Reliance, vice president. He told me that in their Jamnagar, refinery, they have reduced the manpower like left and right. I think there are a handful of people who only operate the entire world's largest refinery. Everything is automated. That's because of the environment is completely controlled environment. You don't expect that dogs and cows and cattle will be roaming inside that environment. You don't expect that the beggars or other people will be there on the roads or within the campus of the refinery. You only expect that robotic vehicles will be going from one location to other locations, and they are controlled. That's why it is possible. So if you ask me, I feel industrial robotics or industrial pipelines are the biggest possibilities for applications of computer vision, which has already been done for last 10-15 years, and it can be further improved also with the help of improved algorithms. Another part which I feel it has great benefit in the medical imaging cases, where you feel that doctors sometimes may not be able to capture all possibilities or all abnormalities in an image, because it requires huge concentration. It requires much more depth of understanding. Okay, so here a computer vision systems or visual surveillance systems can help the doctor. We are not replacing the doctor. We are rather making their life easy just by highlighting the portions or important regions which may be affected, where maybe affected tissues are there, so that doctors or physicians can spend more time into those regions. That's why we call it assistive technologies. That is where I completely agree with the computer vision community that it has great potential, visual surveillance potential. Now, coming back to the original theme, that's then why we need machine learning here. What we have talked till now, that's mainly I was talking about what are the scenarios. Why do we need computer to understand the vision, or why do we need computer to have artificial vision? That we have understood. Now, do you think that if you have the hardware, then it will be sufficient? No. You need machine or computer to understand it. How to make computer understand all these things? So you need efficient algorithm. So we need to develop algorithms that allow computers to learn. In this course, we rather narrow definition of learning. So learn to assign an object or an example to one of the several pre-specified categories. So we'll learn to assign an object or an example to one of the several pre-specified categories. It can be a car, it can be a chair, it can be table. It is also called pattern recognition. For example, if you take this photograph, if you ask people, and if you give them three options, that this is a teacup, this is a face, this is a phone. Okay, people will say that this is a face. Now you extract certain features which are very much relevant and very much common for a facial image, and then you save it through some model. And when another sample image comes and you extract the same features and you try to match it with whether it is matching with some of these existing features or not. Okay. If you do it, it has applications like face detection. Face detection, then whose face? Okay. So objects are here image patches. The classes are face and non-face. So you have objects which are patches like these rectangular areas. Now these rectangular areas there can be millions of rectangular areas within that same image. Now which rectangular areas or square areas, let's take rectangular areas, which rectangular areas are most probable face candidates? Okay, and which rectangle areas are most probable non-face candidates? That is what basically we would like to learn, and we want the computer to learn also. So you have thousands of samples where the face patches or image patches which are ground truth labeled as face. From there you extract certain features and you store them in a specific manner. That becomes your class 1. Similarly, you do it for all classes. And then once the training is done, given an unknown rectangular box, you would like to extract the features and try to match it. That's essentially the first part is learning, and second part is basically classification. It has applications in medical images. For example, here objects are pixels. Classes can be different types of tissues, stroma, lumen. Okay, there are different types of tissues. It can be epithelial cells, it can be an RBC. So objects will be the pixels. So a group of pixels will make an object. Now the objects are labeled as tissue types. Okay, now they are classes. Now when we understood that what we mean by visual surveillance or computer vision, and what is the primary reason that why we need machine learning. Now if you want to add this to why basically we need machine learning algorithms, particularly for visual surveillance, that is what basically we are going to look into. Let me start with some interesting applications of computer vision. One of them is crowd tracking. So crowd tracking is nothing but in a crowded scenarios like this, okay, where heavily, the dense crowd are present. For example, on the right side, an image taken at Puri Rath Yatra, because I am from Bhubaneswar, we have a project where basically we are trying to understand that how density of people during the Rath Yatra creates the administrative problem. So whether this can lead to an accidental situations or not. Similarly, it can be a marathon. Similarly, it can be another political rally. Similarly, it can be for CCTV applications. It can be for marketplace, airports. Okay. So we would like to develop computer vision based monitoring applications that will minimize the human efforts with the help of better information fusion, which can process high volume of video data at lesser amount of time with prompt action, accurate and intelligent decision making systems. If you look into the manual monitoring, it requires precise human efforts. It is error prone and time consuming also. Because if you have 24 hours video recorded and you have to look into the entire 24 hours video, then you need to require another 24 hours video. Okay, that's why it is time consuming. Now, if the crowd is dense, so I'll show you some of the research work which is being carried these days. People actually try to use physics-based model for crowd dynamics. Okay, so crowd dynamics can be, in terms of randomness and energy computed with the help of, models like Gibbs entropy, kinetic energy. You can apply it and you estimate the energy like this. Okay, and then try to try to see that whether the energy is varying over time. Now this will be calculated on the points of motions. Okay, so energy of a pixel, the moving point, can be approximated by a velocity of pixel in motion using optical flow. Optical flow is a very well known technology to understand the motion, local motions. Okay, now, if you would like to get the average energy of the entire frame, you can do the averaging operations, and based on the, the value of the average energy over time of a frame, you can get some information about that, what kind of dynamics is going on within the image. Okay. You can also do some entropy calculations. Okay. So where you do a connected component, instead of doing it for a single pixel, you do a connected component analysis, okay, of nearby pixels, and basically try to make a macroscopic state and microscopic states. Okay, and then the entropy of the frame, you can basically do it for all these regions. Okay. Now, if you see, when we experimented with dense crowd characterization with Gibbs entropy for a crowd like this, which is pretty much what I will say, that it is not random, it is uniform crowd. People are moving at almost uniform velocity. Even though the angle is changing, what you see that energy and entropy both are, entropy is high, but energy is low and the variations are pretty low. The variations are pretty low. Now, if you basically look into this, the same thing for the Rath Yatra image, what you see here, the energy is varying as well as entropy is also varying. Okay. So that is that can be one part of the information which can be used to understand that what is the dynamics of the crowd. So what is the observation here? So if significant fluctuations are observed in interframe energy, it can be attributed to a fast moving crowd with higher velocity. Okay. And if the fluctuations in interframe energy difference are low, then the crowd can be assumed to be moving at a uniform but lesser velocity. So similarly, more fluctuations in entropy indicate varying randomness in the crowd. And for constant entropy, the randomness can be assumed to be less in a video. So these are our observations. It's not necessary that these observations will be true across all videos, but these observations can give us certain clue that how to design the algorithm. Now, moving ahead, what we have tried here is basically to understand it in details, in further details. So here we have tried to apply, because the crowd is dense. We are talking about dense crowds. Maybe maybe thousands of people within maybe a couple of 100 square meters. Okay. So how do you basically handle it? So there we can assume that each and every point, that is optical flow points, they can be assumed to be as a particle in a normal fluid. Okay. And how the flow happens, that can be understood with the help of Langevin model. So we basically formulated this one in a typical Langevin model, and we understood that basically the flow of the segment can be represented, or the force equation can be represented with the help of external force, drift and confinement force, and disturbance. Okay. And with the help of this Langevin model, we basically can predict the position of the groups in the next instance. So instead of calculating optical flow in each and every frame, you can basically save time by predicting it through these force equations, because optical flow is basically a time consuming process. I'm not going into the details of this force equation. These are, these equations have been derived with certain limit, certain assumptions on the actual equation of the Langevin model, and then we have developed a model which was able to detect segment the flow very accurately as compared to the state of the art. So where basically, if you look into it, our entire flow is like that. You have a video sequence, and if you basically apply the window technique, so temporal window frames, you select W number of frames, and then you extract the key points, and you apply a Langevin model based estimation, so you get the positions of the next without going for the optical flow calculations. So the velocities are estimated. That's why I was talking about that, how the new positions are calculated with the help of this velocity estimation and position estimation. So once you estimate the velocity, you can actually get the new positions from the old positions. Okay. And once you know the Is it a polling going on? Okay. So now somebody has raised. Okay. So if you basically apply this, you can actually segment the flow. Now, when we applied this one on different types of videos, starting from Rath Yatra to some, fair gatherings, then we found that we were able to segment it in a better way than the existing algorithms. For example, here, the third row presents the segmentations obtained by our proposed algorithm, where the second row is the ground truth and fourth row is a model proposed by Ali et al. This is applied on Puri Rath Yatra segmentation, and we even found better results there itself. Okay. Now, the tracking that I was talking about up till now, that was mainly for dense situations. Now, if the situations, I mean to say that the objects are not dense, if they are basically, sparse, and you want to accurately see, in the previous case, we were not tracking the objects accurately. Accurately tracking each and individual point was not important in the earlier case. It was rather important that how we can track many such points quickly. Now we will focus to a different set of problem where we want to track objects accurately, and this tracking has to be done on individual objects for a long duration, for a longer duration. That is what we are now moving toward, the object tracking for computer vision applications. If you look into it, the typical tracking and application framework looks like this. So you have a CCTV camera, you capture the frame, or then you extract the key point or track multiple object. Okay. Then you extract the trajectory, so the path, and you create a database. You extract some high-level information from this database, and then do some general applications, like understand that which part of the scene is interesting, whether something abnormality is going on, what kind of summary is this. So toward the right side, 3, 4, 5, they are mainly applications. Okay. But to develop systems for the application, you need tracking to be accurate. That is what basically we must do this. So for tracking, the output of the tracking is a motion trajectory. Okay. And tracking is to localize objects in continuous video frames. And a trajectory is typically represented as a triplet where you have the location of the object in the frame in two-dimensional frame. We are not tracking object in 3D world coordinate. We are basically tracking the objects in image coordinate system. So that's why it is x, y, and t is time. So you have a trajectory where it's a sequence of locations, and every location, the position of the object is at ith position. That tells me. So a trajectory, if you look into its 2D representation, it may not be giving much information to you. For example, when you see the trajectory on the left side, the person was coming from top left corner toward the bottom right corner, but somehow the person actually stayed for some time in the middle, which is not reflected in the trajectory. Whereas when you put it across the time domain, you will find some interesting observation that there is a huge difference in time at a particular location where the xy coordinates are not changing, rather the time axis was only changing. So that tells that the person actually stopped for some time in between and the person was doing something. So a 3D representation gives some interesting and valuable information. Now, once you detect the what are the challenges in tracking? See, the example which I have shown earlier, that is the output. But to generate that output, you will be facing several challenges. Those challenges are related to occlusion. One object is behind another object, so you get occlusion. The object size is very small, sometimes large. It may be environment-wise, lighting changes. It may be multiple objects. It may be the objects are moving very fast than you can process. It may be dense crowd, like I was showing the example of the dense crowd motions. Blah blah blah. There may be many other scenarios or many other challenges. So I'll show you that there are different algorithms which actually extracts trajectories. Now, how to get that which one is the better? So if you have multiple options, then you can actually take decisions based on the multiple options. The same object is being tracked by 3 different algorithms. Okay. So with the help of some fuzziness and with the help of some local decision making process, you are able to understand that which track is better at what point of time. So you can actually fuse this. This is one word with the fusion. Arif et al. They have tried to understand that which track is better. Okay, that's basically given a trajectory. How do you basically get the long duration trajectories? So they actually found that even when I will show you that these original trajectories are very small, but with the help of fusion, we are able to extract these trajectories for longer durations, which is very important. Longer duration trajectories are important to understand that how the object behaved during, say, last 1 minute, last 2 minutes, last 10 minutes. So you require trajectories for the longer period. That is very important. Otherwise, what will happen? If you look into it, these are all small trajectories. These are simple optical flow, Lucas candidate Tomasi feature trackers, but they can't track people for long durations. So with the help of fusion-based techniques, you can actually track get the trajectories for longer durations, and which will essentially help you to take a decision at later stage. That is the objective. Okay. So if you basically do the fusion correctly, you can get trajectory like this. You see that now this algorithm, the modified algorithm, is able to track the object for a longer duration, even if the person actually, goes through several other, regions, and it may be partially occluded at some point of time, but still it is getting tracked. Why it is getting tracked? Because the decision making was improved with the help of a fusion-based technique. Now, once you basically, get the trajectories, then you do the processing. So sometimes during tracking, you will not be able to get the tracks, after a certain point of time. You can predict it. So, for example, you can use Kalman filter-based prediction techniques to understand that what is the possibility of that this object is present in the next frame in this location. Okay. You can also apply that. Okay. So I'll show you some challenging scenarios now. This is IIT Bhubaneswar video we have recorded here, and this was a video on a heavily rainy day, and some objects were moving, and we applied some Kalman filter based improved tracking, which was able to track these objects very accurately, even in the presence of occlusion. And you can see the video quality is also not good. It was raining, heavily raining. What it shows that even if the scenario is very much challenging, if the decision making algorithm is good, then you will be able to track the objects accurately for longer durations. That is what actually you want. But it may not be true always. I mean, this is possible because the number of objects present in this scene is pretty less. Here, in case only 1-2 objects we have seen. It is not possible that always you will get 1-2 objects. You may get hundreds of such objects. So another one video which shows that how you can track. You see that the person was stopped there, so the trajectory got lost. Okay. But overall, if you look into it, with the help of Kalman filter-based prediction-based techniques, it was able to track. It will obviously track in scenarios like this, where the visibility is better. Okay. And it will track. This is again, the videos are from our database, okay, where the objects are being tracked very accurately, okay, even they are being occluded. Now that was basically, you detect an object and then try to follow it, okay, with the help of prediction. Now, the other way of doing the same tracking is basically tracking by detection. So here we apply object detection technique. So, for example, you apply a typical YOLO based architecture, which is like this. I mean, so there are several layers. Okay, you apply convolution layer of a particular scale, then you apply another convolution layer. Okay, and then you apply another convolution layer. So YOLO has its own well-defined architecture, and essentially you go to connection layer and you get the object detection. Now this is well-established architecture which is able to detect objects of hundreds of classes with very good accuracy in individual frame. They do not track, they detect object. Now what I have started here, tracking by detection. So I shall now detect the object in each and every frame, and then I'll try to associate these objects in the frames. So when we have tried this one with person re-identification, we got certain accuracies. Now let us see that how basically this tracking actually works. So you see the detection, how accurately the detection works. So this is a video where you see that this is inside our office building. Somebody is coming, a person is coming, and the person is carrying handbags, and this detection, see, this is only detection, and we have applied a tracking algorithm by association. That's why it was able to maintain the levels. Otherwise, it is only frame by detection. It was detecting each and every frame. The humans, or for example, this girl, she was moving with a mobile phone in her hand. So it was able to detect even that. Okay. Now this sort of tracking is only possible because of the accurate detection mechanisms available with us. So we have set multiple cameras at different floors. This is another camera. It was able to track objects very accurately, even in the longer perspective is changes. I mean, so from long distance areas, so it was not recognizing that who is the person, but it was able to detect that the persons are coming. When they are coming close to the camera, it was able to separate them also. So how we actually did it, basically, this is not our work. This is basically on work published in ICIP 2017, which actually talks about SOTT, simple online deep tracking, which involves detection and association. So detection is basically done by YOLO-based framework, YOLO V3 based network, which only detects. Then we associate the objects, detected objects. It's a post association, post detection state, where we try to associate that the top frame, which is ID number 20, is similar with the next frame with ID number 20 or not. ID number 15 is matched with ID number 15. So that sort of association matching is done here. So you detect it at using the YOLO, and then you try to associate it in other frames. That's called basically detection, then association. So in the frame I, look into then the left side, what happens? You have a video, you have two frames, frame I and frame I+1. You detect both the persons in both the frames. Okay. And then you try to associate them. That is what this paper does. Okay. And it's basically deep association and tracking. So they call it deep association and tracking. So it was really doing very good tracking. If you can look into it, when we applied this, it was able to track the person very accurately. So the level, this one means that this is the person number 1. See here, it got changed suddenly. So that means because of the change of the scale, okay, it was not able to associate. Okay, the association problem. So it's even if you see somebody, if a human sees this one, human will possibly able to take a decision. No, this is the same person going. That's because human takes other information that no other person was there at present in the side by areas. So there is a possibility that the same person is there. But we actually did not use all these informations to correct our result. That's why it has failed here. But if we include that information, then also it will be able to track it, because there is no other person nearby areas. So obviously it has to be the person which I was seeing earlier. So this sort of decision making can be done with post processing. Okay. It can be applied to multiple objects also. So and it was able to detect. So you can see 17 is going again coming, but sometimes it missed also. You see it became 20 now. Okay, because the person came at the front and its appearance got changed. Because of the appearance got changed, the matching with the previous frame got lost. Okay, but it was actually working, pretty decently up to some extent. Okay. These are some more examples of multi-person tracking with the same. Okay, we applied this one on public data sets also. Okay, pets. Okay. You can see it was able to track. Mostly it was able to track. Okay, with levels are maintained properly. Or, sometimes it fails also, but even if you humans see now, because all people are having the similar kind of clothing, it's very difficult to, when they're crossing each other, it's very difficult to manage the levels. Okay, we humans can track one person together. So attention model, you can bring attention model there, then possibly you can solve this problem. If you ask a human, then track all persons, the human will not be able to track all persons. Human will be able to track only one person, two persons, because the attention model. Okay, so if you apply similar attention models, then possibility is that the computer will be also able to do it in a better accuracy. So similarly, when we checked it with other datasets, town center dataset, it was working pretty decently. It was able to track it, okay, the persons with higher accuracy. Then in a closed view scenario where the objects are larger and very close to camera, that is also doing. Then in another scenario, MOT challenges when they are occluded, objects are coming, objects are getting occluded. You see? Indoor scenario, then outdoor scenario. So what I meant to say, it is mostly, it is working. Sometimes it may fail. Anyway, still ongoing research is going on, but I mean, the people are trying to improve this, that how to basically track them. See, the problem here is that there are many people, gathered together, and it's very difficult, to maintain the levels, across time for longer durations. Okay, but still it was doing it. Okay. And then came an improvement because there are certain issues were there with the previous algorithms. Then Zhao et al. Actually they proposed, they came up with adversarial deep tracking, which actually tries to look into nearby areas. That is what I was talking about. That you have a target patch. You don't basically, you have a target patch. You search it within nearby areas. Okay, and then you apply, it's basically RNet and CNet based residual network and convolutional network based in architecture, and it was able to basically track in a better way. Okay, so initially a CNet is fine-tuned by the start frame, and the next is RNet predicts the state of the target in the current frame by utilizing the target patch and the source patches. Okay. And the source patches are usually extracted from the around the, so that's why the source patches, this is basically the information that I am providing to the machine, that I am expected to get the same person in the nearby areas. Okay, and toward the end the CNet performs the discrimination between the matches. So you need to basically discriminate. That is what this discrimination is happening. This RNet is basically trying to optimize the search space. CNet is trying to discriminate, okay, that which is the best one. Okay, this is all about supervised tracking I was talking about. That we know that the objects are detected and objects have been learned a priori, and then you do it. But when you do not know anything about the object, then it comes unsupervised. So unsupervised tracking, it requires unsupervised learning. You do not know anything about the object. Okay, so classification, it comes from the classification background. Basically, learning can be classified into three categories. One is supervised. A supervised learning is the machine learning task of inferring a function from a labeled training data. Whereas in case of unsupervised machine learning, it involves task of inferring a function to describe hidden structures from unlabeled data. So you do not label them, you try to find out the hidden structures. In case of semi-supervised, is a class of supervised learning tasks and techniques that also make use of unlabeled data for training. So when they do the training, they also try to use more of unlabeled data to get to understand the hidden pattern. Okay. So and there are also, for the classification models, there are different types of models. You have parametric models, you have non-parametric models, you have offline models, you have online models. Okay. So if you basically classify this learning based on learning technologies, you have supervised techniques, which is artificial neural network, supervised machine learning, okay, support vector machines, the name-based classifiers. In case of unsupervised, you have digital process. In case of semi-supervised, you may have manifold learning, active learning, constant learning. Okay. Now, in the digital process, because we are talking about unsupervised learning, let's go to that. What are the primary approaches in the digital process? It's a pretty an established method. And we have actually started with a very refined model of this one, where we have tried to use the digital process mixture model. Okay. That is called DPMM. So with the help of DPMM and variable length temporal analysis of motif, we got very good results of. Now this is slightly, I'll just show you the graphical model basically, where how to basically, here we do not know anything about the object. We get only the optical flow portions, and we do not know that. Our objective is not to say that which is the object, whether this is a car, whether this is a bike, or whether no, we do not want to do that. We want to group that the pixels which are having similar characteristics in nature during motion. Okay, and then we basically group it in each and every frame. So that's why that grouping becomes the center of the tracking. Okay, so we have the groups like this: 3, 16, 36, 33, and their paths. We want to extract their paths like this. So this is one of our work, which is done by Dr. Santosh et al., who was a PhD scholar with me. So he actually proposed an interesting extension of the DPMM. Okay, that's we call it modified Dirichlet process mixture model, which is nothing but a refined Bayesian probabilistic model, which was able to track the objects very accurately. This is unsupervised learning purely. So when you tried this one on several publicly available videos, so we thought that this is KLT, traditional KLT. This is mean shift, which are very popular tracking algorithms. But our algorithm is tweak, which we call it tweak. It was able to track in a better way. See, we do not detect the person, we do not detect the object, we do not understand that what is that object. Rather, we want to track, follow that object. Okay. So this is all about tracking. Now, why do we need tracking? Now I will show you that what are the applications of tracking. So we have tracked the objects using AI and machine learning techniques. Now we would like to apply this. If you track an object, what are the objectives of doing this? Here actually I'll tell you why we have extracted these trajectories, because ultimately we would like to do surveillance. Surveillance means we want to understand the scene. We want to understand the meaning of the scene. That's why we have tracked. Now, if you track these objects, you can do a lot of things. For example, summarization or synopsis. By looking into the trajectory, you can summarize that what the person was doing. For example, you can generate binary patterns like this on the right side, and you can say that the person was basically, the x-axis is frame number, and basically y-axis gives the importance. You say that when the importance value changed to this. So with certain importance value, which has been decided, which has been calculated with the help of certain characteristics of the trajectory, it can tell you many things about the characteristics of the trajectory. That whether the person was stuck at that location or something else happened. That is what we are trying to do. And given a long duration video, you do not want to look into the entire part. Rather, you want to focus into that portion of the video where there is some interesting. So where there is some interesting, that can be understood from the characteristics of the trajectories. That is what we are trying to do. So there was a paper which has been published in around 2014, which is a pattern analysis machine intelligence IEEE PAMI paper. What they tried to do, they tried to generate synopsis. Synopsis means, for example, you have a 24 hours video recording available with you. Now, CCTV camera video recording, and you want only to see the important portions of the video where the objects are present. So you try to squeeze the video in time domain. It's a spatiotemporal optimization. You'll have to bring all moving objects. Okay, but you will have to place them in order. That means moving object 1 appeared in time t1, moving object 2 appeared in time t2. So you must place t1 prior to t2, or object 1 prior to object 2, because object 1 has appeared in the original video prior to object 2. So you need to maintain that sequence. At the same time, You also do not want scenarios like this. The same object is appearing 2 times in the same frame. That's not a convenient way. So for example, these two persons, they are same actually. They appeared in the same scene at different times, but because of the wrong synopsis generation, you get a video like this. Two persons which are appearing, they are same, but they are appearing on the same frame. So that's not a good scenario. So this is a typical summarization and synopsis in a generation framework, where basically you do background extraction, you do object detection, you do object segmentation, and then you do tracking, and you create the object database. And based on the objects, interactions with different, other objects, then you try to do the synopsis. Now let's see that how a person who would like to understand that which portion of the video is interesting based on his or her query. Okay. So we call it query guided summarization and synopsis. So you give a query and you only extract those portions of the video where this particular thing happened. Here actually, I will show you some classic example of a binary, object classifier with not binary actually, 3-4 classes are there. For example, we have taken car as a class, we have taken human as a class, we have taken two-wheelers as a class. So we have trained this, and then we have generated the synopsis based on the user's query. What kind of query? User may want to see that I want to see person wearing red t-shirt moving from this location to that location. Show me only that portion of the video. So what you need to understand? You need to understand the person. So human detection, red, that detection. Then the time wise you'll have to go there, and then you'll have to bring that object and fix it there itself. So I'll show you some snapshots of this research work. This has been published in IEEE transactions and intelligent transportation systems from our research group, where you will find this work. This is an interesting work where you see that this is a 1-hour video has been recorded at our campus. Actually, this has been recorded from my residence area, and this is a 1-hour video, morning 1-hour video. I want to see only a 30-second synopsis of the video without missing any single important movement. You see, we have generated these videos, and these times are different times when these objects actually appear. So we have extracted these objects, we have extracted their nearby regions, and then we have pasted them and synthesized this video. And this video is now only of 30 seconds or maybe 40 seconds. And all these objects traveled at different times. Now what it tells, this gives some hope that, okay, I do not need to see the entire 1-hour video. I just need to see only 40 seconds video to understand that how many cars have traveled during the last 1 hour. Okay, so we have applied this to detect the objects here, different types of objects. I am just showing showing you with 3 examples: car, humans, and two-wheelers. You can include n number of such classes and train the model, okay, and do it. Now, what earlier people used to do, you see that how confusing it is. Here, basically, you see the same car is appearing 2 times, 3 times. That was the confusion in the existing work, that PAMI paper I was talking about. You see how confusing this one. It is not visually smooth. The same car is appearing, disappearing, sometimes multiple times appearing, which is not a good example of synopsis. Okay, that is what we do not want. That's why if you look into this result, is much more better. That's because our optimization technique is far better than the other optimization techniques. Some people have actually, to fit many objects, because you cannot bring the objects out of the road. So because if a bus is going on, the bus is big, and if two buses are going on, it will actually occupy the whole road. So you don't get to fit, because your objective is to temporal minimization also. You cannot have a synopsis of 30 minutes for a 1 hour video. That's not a synopsis. Rather, you want a 30-second video of a 30-minute video. That's synopsis. Now, how do you accommodate all objects within the 30 seconds? That's an optimization problem. So it's a spatio-temporal optimization problem. Why it is spatial? Because the location of the road is limited. You cannot put 100 objects there. They will overlap on each other. So you'll have to spatially optimize as well as temporally optimize. That's why it is a very difficult problem. Somebody tried to do it as scale optimization. You look into it. Sometimes the same car is very small. That's not a smooth synopsis. It looks to be artificially created, and it's not a good one. Okay. So some people have tried to do the spatio-temporal optimization. Some cars and other things, they are going out of the road. Okay. We do not want a synopsis like this. Now, once we have implemented our algorithm, then we are trying to understand let's make it more funny. Say, I want to see only the cars. So this one, actually we have classified bus is also a car. So this particular video of the same 1 hour video, it will only show the car-like objects moving. It will not show any other object. So when you give a query like bike, it will only try to show the objects which are of type bikes. The same video when it is processed. Like here, there is a confusion. This is a person was running, a person was walking, it was confused as a bike because the person was from a long distance. So this is a classification problem. Okay. Otherwise, it was mostly working. Now, pedestrian, humans, the same video, it will only show when the persons are moving. See, we have extracted these object trajectories and then we have stitched them properly with a spatio-temporal optimization technique. So detection is done using YOLO detection techniques. Okay, and we have processed them. Now, what are the finer queries can be, or more interesting queries can be something like this. Say, now you understood the paths by looking into the trajectories of different objects. Okay, you got the paths. First you understand the regions. Regions means where the objects are entering into the scene. So there is one region blue, there is one region green, there is another region red. Now you understood the different types of paths. From red, you see that there are two paths. Okay. From blue, you understood that there are two paths. So you get all these different types of paths. And then you give a query like this, more advanced query like this. I want to see objects, all objects going from green region to blue region. You see, this one will only show you the objects which are actually going toward the right. On the same video, it will not show you any other objects going there. And all these objects appeared at different times. So that's more intelligence we are putting into the system. Okay. So essentially, it leads to a framework like this. You have been given a video and you track the object, you do the region understanding, you do the object type classification, you do the synopsis generation. Ultimately, what I want to do, I want to do a textual description of the video, automatic textual description of the video. So my ultimate objective is I'm going further ahead, that given a video as input, I want to generate a textual representation of the video. That may look like more futuristic, but that is what we want. So my CCTV camera captures 24 hours video. Next day morning, it will give me a one paragraph. Okay, I have seen this person with red car came from this location to that location. So I get everything about it. By reading that one page, I got everything. That's it. That is what It's called futuristic. If you are able to do it, then possibly we are solving some interesting problem which the mankind is facing these days at different, places. So something like that. It's more natural that possibly after looking into this, you would like to see that, okay, that possibly you want a comment like this, that it's Dhoni finishes in his own way. Okay. So on the day after looking into this video, the computer will be able to generate a text like that it's Dhoni finishes in his own way. That day, possibly you understand that computer vision has reached its pinnacle. Okay. That is what we want. Okay. So video to text sample results. When we run that, we found descriptions like this: a white van coming from the college building towards the residential zone. This sort of textual descriptions we were able to generate. Okay. Now that was mainly for surveillance applications, visual surveillance. Now look into the other applications of the surveillance, that is traffic applications. Okay. You want to understand the classify the object trajectories, whether a car is moving on road properly or not, whether the car took an illegal U-turn or not, whether a pedestrian has violated the zebra crossing rule or not. Okay. Then you want to understand that what are the most frequently used paths, so that you can take administrative decisions. You know that there are 4-way junctions. So let's assume that you travel to Chennai, you found that there are XYZ junctions, and this junction has certain traffic patterns at a different time. So you want to understand that what will be the adaptive signaling technology that can be automatically the signaling can be automatically done based on the availability of the traffic at different junctions. You do not need a traffic controller to change the signaling. So it will try to understand that what is the density of the crowd or the flow in a particular direction at a particular time, at a particular junction. Then it will automatically take a decision. That is what we want. For that, we need to understand this in the past. All this requires the trajectories to be extracted properly, the objects to be detected correctly, and then you do the clustering. Say, let's take an example like this. This is one London Grand Central dataset. Okay. Now there are 30,000 trajectories on the top image. Do you get any meaning of those trajectories? No. But when we did some analysis with with our own clustering techniques and spatiotemporal clustering, we actually developed a probabilistic model. We would able to understand that and these trajectories appeared at different time. Time was also associated. So we could able to understand that at what time, during what hour, what was the density and which path was more active. So this gradient of color gradient shows that motifs like things, it actually told us that which path was active during what time. So possibility is that you have more number of metro rails or metro trains, cars to be going, because you know that this may be an office timing. Okay, so blue line, it requires more number of carriages than the green line, something like that. And then you can apply this one for anomaly detection. So traffic anomaly detection, like I was talking about, that somebody is taking an illegal U-turn, somebody is taking a wrong turn, somebody is violating zebra crossing. All these things can be done. You know the known patterns, you know the unknown patterns, and then you can train CNN models, you can train autoencoders to understand the errors. Okay, and then you can do the classification. That's basically we're talking about traffic anomalies. Okay. So now, if you want to understand the visual anomaly basically it can be at different levels. It can be at human level, it can be at object level, it can be at interaction levels. Okay. And how do you know that which anomaly, whether the event that is going on is an anomaly and whether that event which is going on is not an anomaly. So you'll have to basically understand. So for that, you can actually always train the system, and you can, given an unknown scenario, you can compare it with respect to the trained models to understand that whether this is an anomaly or an anomaly. Okay. So here you apply fuzzy based, you can also apply fuzzy based rules. Like this, we have tried to do this one for visual anomaly. We found good results. Okay. So for example, we were able to detect this sort of illegal U-turns which is taken. Okay, abnormal U-turn using multi-criteria aggregations. Multi-criteria aggregation means somebody is taking somebody is your one criteria says that okay, I saw a vehicle coming from the top to this one. This is one. The another criteria tells that during that time the signal was green. Okay, the another criteria tells that during that time I saw there were many vehicles coming from the right side. Okay, so and then you fuse them. Okay. That's called aggregation. Okay. The other application of the tracking is re-identification. That's more like security kind of applications, where you have seen a person today, tomorrow that person comes. Okay, you want to identify that whether you have seen the camera has seen this person earlier or not by looking into the face only. Okay, we would like to see based on its appearance fully. Okay, that's called person re-identification. Usually re-identification can be done based on image based. If you get the facial images always, then you can do it. You can have appearance also, appearance plus motion. You can use face recognition guide, you can use deep learning guided methods. Okay. So for example, this is a CVPR 2016 paper where they are trying to basically, with the help of CNN plus RNN model, they are basically clubbing the spatiotemporal relations of the person's walking style, and they are doing it for all known persons. Okay, when an unknown person comes, and they will be basically comparing it with these models. Okay, so what are the main challenges here? The challenges here are that you have indoor and outdoor scenes pose different types of challenges. You have an indoor scenario, you have an outdoor scenario. Somebody is walking with an indoor scenario, camera is very close, you get a bigger silhouette size. The camera is far away, so you get a smaller object size. Okay, and this research also has a scarcity of data set. Where do you get these data sets? Okay, moreover, if you want to do real-time learning and classification, you require a lots of high-end hardware. Either you borrow it through through some third party, or you have your own, but you require hardware for this. Okay. So we have been working on a framework which is called a typical tube re-ID framework, which has been published in IEEE Transactions recently. This is basically which has been not published yet, which has been under review, which basically talks about that you detect the tubes, and then with the help of this tube means that are human, and then how the presence of the human is there across multiple frames, and then you rank these tubes across multiple images. Okay, and across multiple frames. Okay, and then you basically try to predict that which is the person. Okay. This has already been published. One version has already been published. Okay, and they are actually you create a tube like this on the left side, that there is a true positive tube. So tube means the person's appearance at different frames. It becomes a spatiotemporal tubes, and there will be a false positive tubes, that the other person's tubes. Okay, so now you have a tubes for each and every person, and you have a gallery, and you basically try to find match with all persons, and where you find the best match, you try to say that okay, this is possible to the person I was looking for. So this person I have seen earlier. Okay, so that's called basically re-identification. This is an interesting domain. It's an open area of research. Many people have started working on it. Like This is ultimately the architecture that we have already implemented, where you have the true positive cases, you have the false positive cases, okay, and in training, during training, basically you have several such tubes, okay, and you, with the help of temporal window, you extract the features and put them into the gallery, okay. When it comes from the other cameras, okay, you basically try to see that how many true positives you are getting, and based on that you take a decision. Okay.
Good afternoon to all the participants. Good afternoon to all the participants. Myself, Dr. Sridhar, coordinator of this program. I guess sir got disconnected. Maybe within 1 or 2 minutes he's going to connect back. Now, before that, I just want to inform you all about the tomorrow schedule. Tomorrow morning, since tomorrow happens to be the last day of the STTP, tomorrow morning we're going to start our session by 10 a.m. to 12 a.m. We are having Dr. Ramasubbareddy garu, Professor IIT Chennai. Is going to be the resource person tomorrow morning. Sir is going to talk about brain-human interface with machine learning. An interesting topic. So that session lasts within 2 hours, 10 a.m. to 12. Post lunch, we will be sharing the feedback link of the overall STTP, and also we will be having the exam in the afternoon session. link on Flipgrid. You can go to the Flipgrid website and you can give your video feedback. Any of the interested participants can give their video feedback as well. So we'll be sending a mail to then you'll be there. You can record your video feedback. Okay. So these are the few things.
Got disconnected. There was some internet connectivity problem. Am I audible now?
Yes, sir. It's audible, sir. Audible, sir.
Yeah. So actually, I was in my last slide when I got disconnected. Okay. Sorry for this disconnection. So I was talking about this. This was the last slide I was actually talking about. This is tube to tube person re-identification. So basically, where you have a query tube and you have multiple, tubes which are already there in your tube database, and you try to rank them with respect to that which tube it is matching. Okay, and then basically you get the solution that which one is the perfect match. So based on these ranks, you can decide that whether this person is present. You have already seen it or not. So that is another one application of basically tracking Hello. Yeah, sorry. Actually, the network, IIT network today is horrible. It somehow got disconnected. So I am in my last slide. So after that, I would like to, the next slide was my basically my thanks slide to all my students who actually, helped me in, getting this presentation ready. And I have taken some parts of the Professor Jiang's slides and Professor Wang's presentation. And that's it. I wanted to share all of you. Now I shall be happy to answer your queries. Okay. Now the session is open. Please, let me know your queries. Hello.
Hello, sir.
Yes.
Sir, please go ahead, sir. Your screen is visible to us.
Yes, that's why I told you now, because that was my basically last slide. Okay. So I would like to,
Yes.
thank all my collaborators, my students, Dr. Arif, Dr. Santosh KK, Mr. Ajay, Sritam. They are all my PhD scholars, Professor Jans. I took a couple of slides from his presentations, for preparing this presentation. So that's it all I wanted to share with all of you. So now I am happy to, listen to your queries, questions, discussions. We can carry on now. Okay. Yes, please.
So, good evening to all the participants. Sir, I guess you're done with, sir.
Yes, I'm done. I'm done.
Right. So, due to some technical issues at IIT Bhubaneswar, in between once or twice, sir got disconnected. My apologies to all the participants.
Yes.
In fact, sir had informed me once or twice in the beginning, also in between. So, which I'm just communicating to you all. So, thank you for your patient listening, all the participants. So now the platform is open for you to interact with the resource person, sir. If you're having any doubts or any queries, you can interact with sir. It is open for the participants.
Yes. Thank you all participants for joining, and I'm sorry, extremely sorry if today somehow after lunch session there were some network problems in the campus. So in our entire campus network got scrambled 2 times. But I was also able to finish it. The last slide I was there when the last got.
Yeah, sir. By the time you're almost done, no, sir. Not an issue
Yes.
at all.
Yes.
It seems we don't have as of now we don't have any queries from the participants, sir. And sir, on behalf of Lenin Institute of Engineering and Technology, and as well as on behalf of the participants from various engineering institutions around the country, as well as few researchers also, on behalf of all the participants, with your valuable lecture.
Yeah.
So thank you very much, sir.
Thank
And sir, I just want to put forward one small request to you on behalf of the participants, because we have in fact told all the participants that we are going to provide, we are going to maintain a repository of all the material of this STTP.
Okay.
So if you can share this PPT or any other material relevant to these topics, we can provide them to the participants at then.
Yeah, I will share this presentation to you maybe after removing some of the videos and slides because which may be protected to my research. Okay.
So whatever confidential information is there after removing that, if you can share, and if you can share any other material also, you feel like it is helpful for the participants, we are going
Yeah.
to share them with sir, with the
Yes,
participants.
yes. All the research papers which I have been citing here, those research papers, mainly the published research work, which is already there in public domain. I'll share all these materials with you so that you can share it with the participants.
Okay. So because tomorrow is the last day, so we'll do it, sir. After
Yes, yes. Yes, I'll
having
share
the
it by
topic.
today itself, tonight itself.
Yes, sir. Yes, sir. So thank you once again, sir, for your
Yeah, and if the
enlightenment to all the
participants have any
participants.
questions, they can anytime email me. Okay, I'm pretty active in my email. They can write down directly to me if they have any queries on this, any point of time.
Yes, sir. In fact, if you permit us, we leave your email ID open to the participants, sir.
Yeah, I have already opened it. I have already opened it. This is already open to the
Yes, sir.
participants.
So that at any point of time, they can feel free to communicate with you.
Yes, yes, yes. That's the reason that we do all these, courses now. Basically,
Yes, sir.
they
Yes, sir.
would like to communicate with the, community. So that's why this email ID is in public domain. Anyone can communicate. No problem.
Okay, sir. Okay. Okay. Thank you, sir. Thank you very
Okay.
much, sir.
Thank you.
Thank
Thank
you,
you
sir.
all. Thank you all for joining. Okay. And I'm sorry for this network disconnectivity. Thank
Okay, sir. Thank you very much, sir.
you. Okay. Thank you.
Nanchare garu.
Somebody has actually asked a question. I'm working on application of DL in self-driven cars. So he can write that question and to me, I will answer it in email.
Sir, a small token of appreciation virtually to you, sir. Please view the screen once.
Yeah. Thank you. Thank you.
Because
Thank you.
physically we cannot give you any moment
Yeah,
as
thank
of
you.
now.
No, that's all. Knowledge sharing is more important than this token of appreciation.
As a token of respect from our side.
Thank you. Thank you. Thank you all.
Thank you, sir. Thank you very much.
Thank you all participants for listening. Thank you. I thank the coordinator, the organizers, the institute for giving me this opportunity to interact with you. Thank you all.
Thank you, sir.
Okay.
నాన్సరే గారు
Yes, sir.
అది మీరు అనౌన్స్ చేసండి, నేను చిన్న పని మీద వెళ్తున్నాను. ఓకేనా?
Okay, sir. Okay, sir.
నేను మేనేజ్మెంట్ దగ్గరికి వెళ్తున్నాను, మీరు అనౌన్స్ చేసండి.
Okay, sir. So, dear participants, tomorrow morning we have one session, and then followed by valedictory on after completion of the first session. Exactly, it starts at 12 o'clock. Once the valedictory is completed, we will share the feedback link and also the exam link in WhatsApp group and all those things. So you can submit those things. And one more thing is regarding the certificates. So to process the certificates, it may take minimum 1 week. So once we share the details with the AICTE and once they approve the list, then we will release the certificates. Okay. If you have any queries, you can ping me so that I will clarify your doubts. Thank you. We are closing the session for today.